This morning I'm going to be introducing the concept of electronegativity. Now, do you remember a couple weeks ago when I made you watch the Goofy Adams video where they were all living in the settlement and they went to disco and there were like way too many off-color jokes for one, dumb little cartoon like that? But they talked about certain elements being attractive, okay? In particular, it was the story of chlorine. And she, element number 17, had 7 valence electrons, and she desperately wanted to get one more. And she kind of could take an electron from pretty much anybody, because the only element more attractive than her was who? Do you remember? Her sister fluorine, right? Okay. Up there at the top right, element number 9. Okay. And so fluorine got locked up at the house dissolving the dishes, and she couldn't go to the dance. Well, here what we're going to talk about is we're going to talk about what we mean by attractiveness. And that's something called electronegativity. It's the measure of the attractiveness that an atom has for another atom's electrons. So, refresh my memory, electrons have what kind of a charge? Negative, right? So, what part of an atom is going to be attracting electrons at all? The protons, okay, in the nucleus. And so, in a way, the more protons an atom has, the more attractive, quote unquote, it is. But at the same time, the closer that the edge of that atom is to the nucleus, the more tightly drawn in its electrons are, the more attractive it is. And so if you look at the electronegativity between any two atoms, that will tell you when they get close enough to interact with their valence electrons, it tells you how they're going to do that. It tells you if they're going to, if one is going to be super, super strong compared to the other one and it's going to just steal the electrons away like chlorine did from sodium, or if they're both going to be relatively strong, in which case they're going to end up sharing electrons, or if they both happen to be fairly weak, then they're just going to very freely share their electrons, and their electrons are going to flow from atom to atom to atom. So if you will take a look at this table of electronegativities. Somebody hunt around on here and see if you can find, well, take a look at it and see if you can spot a few trends for me. What are some things you notice?
All of the noble gases except for are
exactly. And that tells you that they are not attractive for other electrons at all. Remember, the noble gases, the thing that makes them noble is that they don't form bonds with other atoms. Okay? Xenon is a special case. What's something else you notice? Like where certain numbers tend to be clustered. Where are they high? Where are they low? Okay? There are some high ones in the middle, and you see that they're kind of shaded. The really attractive ones are shaded kind of purple or orange. Where are the most attractive ones? They're in red here, right? So there's fluorine, okay? And there's her sister chlorine, bromine, iodine.
the halogen.
The halogen, exactly right, okay? Now, in addition to them, oxygen is also very attractive, and you should hopefully by this point know that oxygen is very reactive with lots of things. Nitrogen is also fairly high. Where are my lowest ones besides the zeros? Okay, they tend to be on the far left, the alkali metals here. They're all less than 1, right? Which one of those has the very lowest numbers? Francium, exactly right. Okay. Next to the noble gases, francium is the least attractive atom. Now, so in other words, the trend, if we're looking at electronegativity, things tend to be more electronegative as you go this way up the table, and they tend to be less electronegative or less attractive as you go this way. How about within like a single group? If you just look here at the alkali metals, where are your most attractive ones? At the top or the bottom? At the top, okay? And your halogens, where are your most attractive ones, top or bottom? Top. Okay? Now, to a degree, that kind of makes sense, but it kind of doesn't. Because if it's protons that are making an atom more attractive, wouldn't the ones down here with more protons be more attractive than the ones at the top? One would think.
Well, you said that they want to be closer to the nucleus.
They do want to be closer to the nucleus, but at the same time, as I'm coming down here and adding protons, what else is getting added on? More shells. And so each time you go down a row in the periodic table, you're adding a new energy level of electrons. And so by the time you're down here with astatine, you've got 1, 2, 3, 4. You've got 6 layers of electrons between anything outside there in the nucleus. So as much as an electron might want to get close to a nucleus, there's just no way. Okay? It's kind of like, you think about somebody, they may be like, super movie star hot, but if they're wearing like, 7 or 8 or 9 layers and they look like, the blueberry girl from Willy Wonka, you can't really tell that they're hot, right? Maybe they're attractive, but who can get close enough to find out? So what we're looking for is we're looking for the difference in electronegativities between any 2 atoms that are going to form a bond. So, 3 different possible situations. First possible situation, if the density is less than 0.5, then the bond is what is called nonpolar covalent. So in a nonpolar covalent bond, what that means is that the electrons, instead of being stolen by one atom or another, they're shared equally. Okay? It's like, imagine 2 fairly evenly matched people. They might both be really strong and they might both be really weak, but you put them on the end of a rope and you have them do tug of war. If they're evenly matched, the match could go on forever, right? Because they're both pulling about equally the same. So that's what's happening here. They're both pulling on each other's electrons fairly equally, and so neither one of them grabs the electrons completely and totally to themselves. They're shared evenly. Okay? Look at the O2 molecule. Okay? So if I've got 2 atoms of oxygen, okay, here's an oxygen, here's an oxygen. Each one has an electronegativity, according to that table, of 3.44. Well, when I find the difference, it's 3.44 minus 3.44. Hard math, what's the answer? 0, right? Is 0 less than 0.5? Yes, it is. Okay? 0 is nothing, right? So any electrons that are in a bond between these 2 are going to be shared evenly, and the molecule is going to be what's called nonpolar covalent. Now, think ahead a little bit. If I've got something called nonpolar, what does that tell you I'm also going to have eventually? Polar. Okay? And we'll talk about what polar means with this next example. Questions there so far? All right. So, next rule, if the difference in electronegativity is between 0.5 and 1.6, then you have what's called a polar covalent bond. Now, in a polar covalent bond, one atom is going to pull a little bit more strongly than the other one. So they're still going to be sharing electrons, but it's kind of like, do any of you have a big brother or big sister? Okay. Have you ever had to quote unquote share with them? You know how fair that is, right? They're bigger, they're tougher, they get to share it a little more equally than you do. Or maybe you were the whiny little brother, little sister, and so they got in trouble if they didn't give you a little bit more. But in either case, the sharing is not perfectly equal. And so you get what's called a polar molecule. Now, a polar molecule, we're not talking about like North Pole, South Pole cold. We're talking about like North Pole, South Pole of a magnet. Okay? Or the positive and the negative end of the battery. A molecule where the electrons are not being shared evenly is going to have positive parts and it's going to have negative parts. It's going to have slight positive, slight negative charges in different parts of that molecule. An example I want to show you is HCl, hydrogen chloride. So if I wanted to find the difference in electronegativity between these, I'm just going to take 3.16 minus 2.1 What's my answer? 1.06. 1.06 is greater than 0.5, but it's less than 1.6. So what I'm going to have here is I'm going to have this more attractive atom right here, chlorine. It's already going to have 7 of its own electrons. Hydrogen is going to float in, and it's going to have 1 of its own electrons, and they're going to end up sharing them, but chlorine's going to pull on it a little bit more. And so what that's going to result in is this end of the atom is going to have a slight negative charge to it. Okay, kind of like the flat side on a AA battery. This end down here is going to have a slight positive charge to it because the electrons are being pulled more this way. And that's going to be super important. We'll talk about why soon. Okay? Any questions on how we got that? All right. Final situation. If you have a difference in electronegativity that's greater than 2, then the bond is what is called an ionic bond. Okay? What word do you see in the word ionic? Ion. Does anybody recall what an ion is? In an ionic bond, one atom steals 1 or more electrons from another atom. This is what happened with sodium and chlorine. They got out on the dance floor. She ripped his valence electron right off and added it to her own code. I see this a lot, typically in high school. You see a girl walking around wearing a Letterman jacket, and it's like, way too big for her because she convinced some poor boy to let her wear it around all the time. So he's standing around cold and she's like wearing his jacket. It's kind of the same thing, except instead of a jacket, she stole his electron. And he's lucky if he ever gets it back. Okay? And so the atoms involved, because electrons get stolen, those atoms are no longer neutral. You make positive and negative ions. Okay? And the example here I've got is sodium and chlorine. I don't even have to do the math right there to tell you that 3.16 minus 0.93 is going to be a lot bigger than 2, right? Because 3 minus 1 would be 2, and I've got more than 3 and I've got less than 1, so I know it's going to be more than 2. If you want to math it, you're more than welcome to. In this case, chlorine's got her 7 valence electrons. Sodium, he's in column 1. He has 1 valence electron. She is so strong and she is so attractive, she literally steals his electron and doesn't even let him have it anymore. Now, what that means is that he now has, if he's sodium, he has 11 protons, and he only has 10 electrons. So now, he has a charge of +1. Okay? Chlorine, because she has 17 protons, and now she has 18 electrons. That was weird. She now has a charge of -1. Okay? These are ions. Ions are atoms that are not neutral. They either have a positive or negative charge. If you want to get really nerdy about it, actually this is a really nice thing to know. We call a positive ion, it's called a cation. If you like cats, it's really easy to remember that one because you have positive feelings about them. If you hate cats, I'm sorry, you just failed chemistry. That's a joke. Negative ions are called anions. Okay? That's not onion spelled with an A, it's anion. The way I remember this one, your parents sometimes get on your nerves, especially because they always want to know where you're going, who's there, what are you doing on your phone, okay? Why are you up so late? Who are you texting? Stuff like that. It's because they care about you. It's because they want to keep, ready, here it comes. They want to keep an eye on you. So you have many feelings yet. Use the jokes though, so I'm sorry. So, there are a few more cases actually, and one of them, if your difference in electronegativity is somewhere between 1.6 and 2.0, and a metal is involved, then it's always going to be ionic. However, if the bond only involves nonmetals, then you're going to have a polar covalent bond. Because if you remember, and I'll throw it back up here real quick. I'll come back, don't panic. Coming back to this, your nonmetals are the ones that are to the right of the stairs here, and they tend to have much higher electronegativities. They also tend to take electrons and hold on to them much more tightly. Metals tend to be weak ones. And it's not that it's their fault, it's just the nature of metals. Metals, because they've got only one or two electrons in their valence shell, they tend to be fairly far out from the nucleus of the atom. And so it's, if I can throw another metaphor at you, it's kind of like football. If I get a football, and here, let's throw the old moleskin around here. If I get a football, and I receive it, and I start running, what's the worst possible way that I can carry that football? How about way out here? Oh, I'm running. Got my football. Okay, because what's going to happen? Somebody's going to strip it, right? Okay? They're going to take it away. It's going to be a turnover on a fumble or something. So you want to hold it in nice and close. Metals hold their electrons way out here. Nonmetals, because they've got more protons, they draw them in nice and close. And it's much harder to take an electron away from a nonmetal than it is from a metal. Metals are not good football players. A few more slides to go here. So here's some rules of thumb for you. 99% of the time, if you have two nonmetals, they are going to be forming a covalent bond. Sometimes it's polar, sometimes it's not. For you to figure that out, you do have to look at their electronegativity. But nonmetal with nonmetal is almost always going to be a covalent bond. A nonmetal with a metal is 99% of the time going to be an ionic bond. Now the one case we haven't talked about at all yet is what? Metals with metals, okay? Metals forming bonds with metals, they form something special called a metallic bond. And in a metallic bond, what happens is that neither one of them really have a really tight hold on their electrons. The way I like to describe this, take the same guys who are terrible at football, send them off to college, make them all live in a dorm together. Okay? What happens in a dorm is that the idea of mine versus yours kind of fades away, and it's pretty much just, oh, I see a thing, hey, it's mine. And so, I remember several times living in the dorm, and I'd be sitting in the lobby, and somebody would come walking through the lobby, and I'm like, hey, that looks just like my shirt. Oh, hey, that is my shirt. I haven't seen that in a while. And it was not a big deal because, I did it too, but it's like everything just kind of flowed freely. I had this will tell you how old I am. I had just bought a Super Nintendo game called Killer Instinct when I went off to college. I didn't see that game for like a year and a half. I mean, people played it all around the dorm. I knew it existed, but it wasn't in my personal possession. Same way with metals. They don't really care too much about personal property. Electrons flow from atom to atom very, very easily. Now, what do you know about metals? What's a very well-known property of metals? They are excellent conductors. This is why. Because the electrons flow very, very easily from atom to atom, that means energy can get very, very easily from atom to atom. Whether that's electrical energy or whether that's heat energy. Okay? What's another property of metals? When you look at them, how can you tell it's a metal? They're shiny. It's the electrons flowing freely through them that gives them that shine. Okay? It all comes down to the electrons.